crossing the streets, moving through a crowd, something that for most of us seems completely normal and simple, is still an everyday challenge for about 250 million people around the world. For a blind person, mobility is still one of the biggest issues they have to face.
At the 5G Academy, in collaboration with New York University, we have explored the use of advanced 5G technologies to augment the cognition of visually impaired people. We started from recent developments at the NYU Reactive Lab, where wearable sensors and processing devices are used to enrich situation awareness.
We proposed a high-tech system that incorporates a whole range of new technologies into a wearable device in the guise of a backpack, where an array of sensors, inclusive of stereo cameras and microphones for computer vision and audio analysis, and an ultra-fast GNSS receiver for high-accuracy localization, are all mounted and streaming data to an embedded system.
Inspired by Reactive Labs technologies, we have developed Horus, a solution that aims to significantly improve the usability and portability of real-time augmented cognition devices by leveraging 5G advances to seamlessly move all the processing-intensive tasks to the cloud.
For advanced wearables such as this project, 5G networks offer at least two groups of important technologies for providing cloud connectivity. The first are new air interface technologies, such as transmissions in the millimeter wave bands and massive MIMO, that enable higher data rates to support uploading rich sensor and camera data at very low latencies. The second is mobile edge computing, which brings cloud resources closer to the network edge. Both technologies are new, and we're very excited to work on this project with the Italian 5G Academy to validate these methods in a challenging and valuable application.
Horus is a medical device designed for mobility assistance, consisting of a pair of smart glasses and a vibrotattile belt able to suggest the presence of obstacles, its direction and distance.
The camera used for the Horus project is a stereoscopic camera. The camera captures images of the surrounding environment, and the data, elaborated by an edge cloud, return as a vibrotattile feedback and audio synthesis. The first one will be sent to an abdominal smart belt, therefore a specific vibration will indicate the position of the obstacle. The second one instead will be transmitted to a bone conduction headset integrated within the smart glasses.
Per un non vedente è fondamentale muoversi in autonomia e sicurezza. Avere una cintura che possa dare degli impulsi di segnalazione di ostacoli potrebbe essere davvero fondamentale, e avere la segnalazione con una vibrazione potrebbe essere davvero una svolta importante, in quanto le nostre città già sono piene di suoni e rumori, e ulteriori suoni potrebbero creare soltanto problemi alla persona disabile visiva.
Our device exploits the capabilities of the latest generation of video detection software, which is capable of identifying objects in captured videos in real time. Thanks to the innovative machine learning and artificial intelligence algorithm, we are able to process the data with extreme precision. The 5G connectivity allows us to connect to the far edge cloud in real time, reducing the latency, thus meeting the need of reliability and the security of the mobility assistant device for visually impaired people.
Thanks to a business model more focused on the customer journey and customer experience, and above all to the opportunities provided by 5G, it has been possible to cut costs in the production phase.
Through our solution, the user acquires new perceptive capabilities and a greater awareness of space. This new source of data increases the feeling of safety when moving in an unfamiliar environment.
Horus is only the first step towards augmenting the capabilities for visually impaired people. Cortical vision processes using wearable sensors and local processing devices aim to restore visual sensation by directly applying electrical stimulation through microelectrodes implemented in the visual cortex. One could think of the use of 5G to move the local processor to the cloud. Information would be collected by the camera, sent to the cloud for processing, and delivered back in the form of stimulation patterns to the cortical implant.
In the context of cortical visual prosthesis, 5G can be a powerful technology to help blind people. Today, cortical visual prostheses are compact portable devices, therefore they only have limited processing capacity. The idea of using 5G is interesting because we could transfer data in a cloud for high-performance processing in real time. One could imagine, therefore, to control in real time the stimulation parameter on the patient based on the information recorded. from the patient and therefore improve the performance. This is a crucial step to implement better device in artificial vision.
Immagino Horus come un nuovo senso, in grado di aiutarci a percepire ciò che non vediamo, facendoci acquisire maggiore autonomia e sicurezza nella nostra quotidianità.